I need to.
Hello.
You already got it?
Yeah.
Hello, Mr. Ryan. Are you alright? Yeah. Good. So remember yesterday we talked about the bricks problem. Yeah. Bricks layout, right? Remember?
Yeah.
Bricks layout. So what's the problem? Can you remind me? So we have a look. Okay, that's it. We have a wall, yeah, and then each wall is. Okay, I need a pen, a better pen. So each wall, for example, like the bricks are height of 1 unit. Okay, so that's height. So that's 1, 2, 3, 4, 5. H equals 5. And the width, yeah, width, let's say equals 5 as well. And then we have two kinds of bricks, 2 and 3. Okay, 3 and 2. Okay, 3 and 2. And you can only place the bricks horizontally, yeah, one by one horizontally. So how many ways of placing the 5? Yeah, because 5 equals 3 plus 2 or 2 plus 3. You can pick as many. For each brick, you can place as many as you want. So there are unlimited number of each bricks. Okay, so this is kind of the unbounded knapsack problem. Yeah, knapsack. So what does it mean? Is that you want to this knapsack is the capacity is W, right? And then we have these different items. Each item, for example, this item is size of 3. This item is size of 2, and we want to fulfill the knapsack with these two kinds of items. But for each item, there are unlimited number of these. You can choose unlimited, right? So this is 2, okay? So 2 ways, 3 plus 2 or 2 plus 3. So this is 2 way. And how many possibilities we can place in the second row? How many possibilities? The first one is 2, and the second one is how many? The same, yeah? Is it the same? Ryan? Yeah, okay. So the third one.
32.
Yeah, how do you come up with this number?
So, I times 2.
Times 2, times 2, times 2, times 2. So 2 to the power of 5, right? Because the number of ways to place the first row, second row, third row is independent. They are independent, yeah? So the combination is multiplied. So 2 to the power of 5, okay? So yesterday we talked about the top down. So if we use the F width, okay, F width to represent the number of ways to put the bricks, yeah, put the bricks in the size W. So do you still remember? It's equals to what? It equals to the sum of F W minus I, where I belongs. Yeah, remember this symbol belongs to. It looks like a E. Yeah? Belongs to the bricks. Yeah. Okay. And let's say Fk is smaller is 0 if k is smaller than 0, yeah? And Fk is 1 if, okay, so we can just say F0 equals 1, okay? Okay, okay?
Yeah.
Okay, so yesterday we talked about this, the recursion with the minimization. We use the cache, remember? Yeah? And then we can do this in recursion to solve. In order to solve Fw, we need to calculate recursively F function with a smaller value, right? So this is top down. Okay, so let's do it bottom up. We can use use another approach to implement this to solve this dynamic programming algorithm, right? So like defined, let's say this is called function, and we have the number of bricks, and we have W, we have H, right? Alright, right? Look. So now we want to define another function. Define let's say Fn, okay?
Yeah.
dp, this is an array, yeah? We want to store this number. The first one, dp0 is what? Remember?
Is equal to 1 plus 0 times n.
Yeah, the first one is dp0, yeah? Plus
0 times n.
What does it mean? What does it mean? What does it mean here?
So you plus 1.
So this is...
So your dp is equal to 1 plus 0 times your width.
Yeah, so this will come up with the array, which is 1 and then 0, 0, 0. How many zeros here? How many zeros here? How many zeros here? Come on, n. And then that's 1, yeah? dp1, okay? So that's what it means. dp is this array. And then we want to calculate this dp array from this is dp0, yeah? dp0 is this value. And we want to calculate this one by one, here dpn, right? dpn. So the result is dpn, right? Got it? And we can also use which number? dpn is dp1. The last number of the array, which is, we usually use the negative number, which is what?
-1.
-1, well done. So this is bottom up. Why is bottom up? Look, we are calculating the dp from the smaller number to the upper number. The top down, what's the top down? We want to calculate dpn, but then we need to go back to the lower, to the dp with a smaller value, yeah? So that's what it means. So now dp, then I can do this for I in range
n+1.
n+1, yeah, because this is up to n, okay? And then we want to go through the bricks. What's fj in what?
In bricks.
Yeah, we want to go through the bricks, but we want to make sure that the capacity is bigger than the bricks, yeah. So we need to check if what?
If I is
Bigger
or equal to j.
to j, okay. And then we need to sum up with that thing, yeah. dp I plus equals what?
dpi minus j.
Yeah, I minus j. Remember this fn equals sum of fn minus I, where I is the bricks, yeah, is the bricks. Okay, so that's what it means. And then return
dp minus 1.
or dp what? Or dp what? dp minus 1 or dp what? Remember?
Width time height.
The dp minus 1 is the last element, which is what? dp what? Remember, we just talked about dp what? N. It's the same, yeah? Yeah, this is the same too. And then we know the fn, so return fn.
Width time height.
Yeah, f width is the times time height. Remember, f width is f5 is 2, right? Yeah? And times time, what's times time height mean?
The power.
Okay, 2 times 3 equals what?
8.
8. Because 2 times 2 times 2, 3 2's times together. And you can also write it as power what? 2,
3.
2 comma 3. Okay, it's the same thing. 2 to the power 3. Yeah, 2 to the power 3. So it's 2 to the power 3. What's the time complexity?
AWH.
WH, well done. We look, this is N, yeah, W, yeah, we're calling that W. Actually, this is W. H, yeah, H, F, W. And then H, this is the side, actually not WH because, not WH, WN. N is the number of bricks, okay? So it's OWN, okay? Times H, let's call it, okay, 2 to the power of power function, okay? 2 to the power of, let's say x to the power of y, x to the power of y, the complexity is log y, okay? So actually the complexity will be OW times N times log height, okay? So that's the complexity. N is the number of bricks, yeah? W, this is W, N, and because at last we need to times with the H, which is the height. And if we want to consider x to the power of y, compute this, the complexity will be OH, yeah? O log H. Why is that? Why this is power? Remember, we talked about this. 2 to the power of 100, what's the time complexity? How many times you need to times 2 to the power of 100?
100 times.
That's linear. You don't need to times this. You can do this. What? Let's consider this. 1, 2, 3, 4, 5, 6. How many? You can do this times 6 times. That's 6 times, right? Yeah. But how about if I tell you I can do this? 2 to the power of 6 equals what? 2 to the power of 3 times 2.
16.
No. 2 to the power of 3 times 2, right?
It's 8 times 2 is 16.
So what does it mean? 2 to the power of 3 times 2. So how many times of doing that? 2 to the power of 3, you only times 2 times. Yeah? So you can get this 2
It's
times.
8.
And then times itself.
16.
So how many multiplication are we talking about? Look, if you do this 6 times, you get 1, 2, 3, 4, 5. 5 times, okay? You times it 5 times. But here, you only times it how many times? 3 times. Because I can calculate this. This is 2 times, yeah? 2 multiplication. 2 times 2 times 2, yeah? Yeah? That's 8. And 8 times 8. So that's 1, 2, 3. 3 times. So which one is better? Which one is better? This one, yeah? Because it uses less multiplication. That's what I mean, yes. If a to the power of b, if b is an even number, if b is even number, I can always do this. A to the power of b2, and then I do this. Right? Look, right? If b is even number, I can do this. Because this uses less multiplication, and I can save half. If b is odd number, so if b is odd number, it equals a times b minus 1, right? Look, yeah, because look, there b if it's 2 to the power of 3 equals what? 2 times 2 to the power of 2. That's it. Because look, 3 times of 3 2's times together equals 1 2 times 2 2's, right?
Yeah.
Okay, so what here a to the power of b. We want to calculate it. The term complexity is log b. Okay, got it?
Yeah.
Okay, that's it for today. Thank you.
Bye.
Bye bye. We're done. Good job.